In this module and the subsequent 5 or 6 modules, we are going to talk about one solution method which is called as similarity method. This, along with the integral method, which we will see after this, are basically two very good solution techniques that can be used to solve the boundary layer equations. Scaling analysis gave us an order or estimate of quantities. Say for example, we could say boundary layer thickness delta over x is of the order re to the minus 1/2. Scaling analysis was able to give me something like this. So, this tells me that it is going to vary as re to the power minus half, but it does not tell me the value of this coefficient here in front, which is important for us to find out how exactly delta is going to vary. So, delta could vary as delta by x could be equal to 5 divided by re to the power 1/2 minus 1/2, or delta by x could be 4.8 divided by re to the power minus 1/2. Whatever be it, this coefficient dictates the rate of growth of the boundary layer. So, this is delta as a function of x, correct. So, now the accuracy of the prediction of delta depends on the accuracy of this coefficient. So, whether it is 5 or 5.12 or 4.8 or whatever be the coefficient, how accurately we are able to determine this coefficient determines how accurately we are able to predict the variation of delta, which means variation of coefficient of friction, which is also proportional to reciprocal of Reynolds number, and therefore, variation of wall shear stress, etc., so on and so forth. These are all quantities which we require in engineering applications. So, engineering quantities, though we say that delta etc. may not be of great use, Cfx, tau wall of x are quantities which are important from engineering point of view. So, the accuracy of prediction of delta dictates the accuracy of prediction of this, which means whatever I do, if I fit experimental data to set of experiments which have been done, the experiments have to collapse to the form delta by x is of the order re to the power minus half. It has to collapse that way. Once that collapse is done, the manipulation of the experimental data, whatever procedures are there, you would get the slope or something like that, which gives me the coefficient, which could either turn out to be 5, 4.12, 4.18 or whatever it may be. Now, these two solution techniques, so scaling gave me this similarity method and integral method. This is what we are going to see today, and about 5 modules we are going to continue, and the last one is integral method. Similarity method actually is a little bit more difficult in terms of the solution procedure, because you are going to convert the set of ODEs to a partial differential equation. Even integral method does the same thing, but there is distinct advantage and ease of handling things. Integral method basically integrates everything over a domain, over this is y, and this is x. There is integration carried out of the PDE to ODE. Integration of the PDE over y is equal to 0 to some y is equal to h, much greater than delta or delta t, and then you convert this to an ordinary differential equation. Then you assume profiles. So, assume profiles for u of y or t of y comma x. That means, you say that this is going to vary as say polynomial or sinusoidal or any function, etc. You choose the function. This also could be any function. Once you choose this, there would be, say for example, we take a eta plus b eta square plus c eta cube plus d, okay, where eta is equal to y over delta as a function of x. Okay, this is just eta is just a dummy variable, it has no physical significance. We are going to have another eta which is very different in a similarity method. So, the job would be, okay, I choose this profile saying that my velocity is going to vary this way inside the boundary layer. So, the velocity profile is this one. Very good. But what are this A, B, C and D? These have to satisfy boundary conditions which are for the flow. A, B, C, D from boundary conditions which are specific to the flow problem. What are the boundary conditions? Those boundary conditions would be what are there for the boundary layer equations. That means, at y equal to 0, u is equal to 0, no slip. At y equal to delta, u is equal to u infinity, second boundary condition. So, I have a flat plate, this is delta as a function of x, this is my velocity distribution, polynomial function a eta plus b eta square plus c eta cube plus d. I need 4 boundary conditions. So, I have to think of physically correct and mathematically, and have to be able to track make them mathematically. I have to put them in a form which can be used mathematically, and once I use, so n unknowns in coefficients, n boundary conditions, then only I will be able to solve to get A, B, C, D. Therefore, it gives me A, B, C and D. It might require matrix inversion, it might require very complicated algebra, does not matter, I will get A, B, C and D, and therefore, I would get u of y, which means I would therefore get my boundary layer thickness as a function of Reynolds number, and also I would get other quantities which we will define later as momentum thickness, which is delta 2 as a function of Reynolds number, displacement thickness or delta star, which is a function of Reynolds number. So, we will get several of these things. So, let us not worry about it at this point of time. What I am trying to tell you is the integral method can you decide the function, you are the boss. Once you decide the function, the boundary conditions are given by the problem. You can have some case there is V is equal to 0 for a flat plate solid wall, but suppose I have there is blowing of air through small pores in the wall, okay, in turbine blade cooling, just to make the boundary layer grow. If this was the original boundary layer with V equal to 0, this is V greater than 0. When I am blowing air into the flat plate, the boundary layer is going to go up. This is done artificially. So, this is with concept called blowing. The boundary layer is thickened, in which case VW at y equal to 0 is not equal to 0. In fact, VW greater than 0. So, boundary condition at wall would be at y equal to 0, u equal to 0, V is equal to VW not equal to 0. So, this is specific to a blowing problem. Suppose I have a problem where I want to reduce the boundary layer growth, I want to reduce the resistance to heat transfer. So, this is with V equal to 0, and if I suck out the fluid, working fluid with a negative velocity, this is VW greater than 0, then my boundary layer is going to become thin. This is called suction. So, when I have suction, I would get boundary condition at wall with suction y equal to 0, u equal to 0, y equal to 0, v equal to VW less than 0. Unlike solid wall where v equal to 0. Each of these boundary conditions would give me different coefficients because it has to satisfy the physical problem. Therefore, my accuracy of solution depends on how accurate I am having these boundary conditions specified mathematically. Some other boundary conditions may not be very obvious, they have to be thought of and written. So, 4 boundary conditions are needed. So, these 2 are obvious, other 2 we have to think a little bit and then write. So, integral method that way is reasonably straightforward in terms of the procedure. You require good amount of thought in using the boundary conditions. The profile is your choice. It can be used for any type of problem, not restrictive. So, integral method is not restrictive, but it is less accurate because of the profile fit that we are taking. Okay, so, not restrictive, all classes of problems you can do, except that the complexity may change according to the boundary conditions. Similarity method, on the other hand, is a class by itself, because what happens here, the concept we will explain now, and then we will go to the derivation later on. See, what we are trying to say is this boundary layer profile delta of x here, I have a velocity profile at x1. Let us keep in mind our coordinate axis x and y. This is my velocity profile at x1, this is my velocity profile at x2. Please remember, we are showing very highly exaggerated plots. Okay, so u of y here, this is u of y. This profile at x2 and the profile at x1, what are the limits within which it acts? U is equal to 0.99 times u infinity at y equal to delta. So, the edge of the boundary layer everywhere is this u equal to 0 at y equal to 0, right. So, both these have the same starting value and the same ending value for the velocity. One thing is, at x1 boundary layer thickness is delta 1, therefore, the change du by dy in very gross way is u infinity minus 0 divided by delta 1. At x2 boundary layer thickness is delta 2, du by dy is u infinity by delta 2, and because delta 2 is greater than delta 1, du by dy at x2 is less than du by dy at x1, because delta 2 is greater than delta 1. Okay. Now, the point being, the profiles are exactly of the same shape, same nature, except that it is altering its shape a little bit. It is getting stretched in the y direction, and therefore, it is getting compressed in the x direction. Conservation of mass tells me that whatever is the mass flow rate, that has to be satisfied. So, you do not have any mass holding or mass loss from the control volume. What is changing is the effect of viscosity is getting propagated up to a greater height. Delta 1 becomes delta 2, which means the slowness of the profile is getting propagated to a greater height. But what we are saying is, whatever mass is coming at this section, same thing here, except that there is a small mass going out, we are going to argue that these profiles at x1 and x2 look similar. They are not the same. Please remember, they are not the same. So, this is something students have to be told. The similarity is typically given in textbooks without much of explanation, or the explanation is little difficult for students to understand. The similarity variable which we define is a mathematical thing that we will come to later. The physics of it is that the profiles are similar in nature, they are not the same. That means, value of the velocity, say for example, u and v at x1 and some y1, same thing u and v at x2 comma y1, the same y location. Let us say I am taking this point at y1 distance from the wall. So, this point velocity in this profile and this profile are obviously not equal. We are not saying that the values are equal, we are saying the profiles are similar, and therefore, something which is dependent on x and y, therefore, we are having a PDE. Because velocity is a function of x and y, we are having a partial differential equation. Suppose I absorb the dependency of x and y in a new variable called eta, which we call as a similarity variable. Please note, this eta has nothing to do with this eta. This is eta is a non-dimensional variable y by delta. So, this eta is just, unfortunately or fortunately, the nomenclature used in books is the same. This eta is local y over delta. This is 1 y divided by delta at that location, that is my eta. At next location, this y divided by a larger delta, that would be your eta. So, this has nothing to do with the similarity variable. This similarity variable is such that it takes care of the effect of both x and y variation. Therefore, what happens? My partial differential equation, which had two independent variable, now has one independent variable. Therefore, this becomes an ordinary differential equation. So, because eta is a function of x comma y, and therefore, PDE becomes ordinary differential equation. What it means is that all the profiles that you have at x1, x2, x3, x4, x5, all the profiles can be collapsed to a single profile as u of eta, which would say that when eta is so much, it could be because of the change in y or because of the change in x, does not matter. If you pick an eta, that eta would take care of a family of locations, family of coordinates, where which correspond to the same eta, and these profiles can be collapsed into a single profile. All profiles can be collapsed to a single profile. This is the beauty of similarity method. So, with this philosophy or background in mind, we will start with the actual derivation. It is a slightly mathematically involved procedure. As teachers, I would advise you to go through this procedure systematically, and when you solve this Blassius profile in class, you will at least have a background of where this has come from. So, students might not be needed to go through this entire derivation, but when you get an equation f triple prime plus 1 half f double prime equal to 0, which is what is the end equation for Blassius profile, you know where exactly it came from. It is one special case of the family of equations that we are going to derive today and in the subsequent modules. So, let us get started. So, actual magnitude of u at some y, we saw this, the magnitude of u and v at some y1 at location x1 and location x2 are different, but they are related by a stretching factor s of x. So, let eta bar be equal to y into some s of x, where s of x is called as a stretching factor. This is just mathematics right now. This is the so called similarity variable. I am calling it eta bar on purpose because there will be some constants which will come in front of equations. Then we will absorb that constant with eta bar and then call it eta. So, the final equation will be in terms of eta, but for starting we are going to call it eta bar. Otherwise, you would have some coefficients which are going to stick, which are only numbers, which we can absorb in the variable eta bar. Okay. So, u therefore, based on this, u of x comma y will become u of eta bar, v of x comma y becomes v of eta bar, PDE in x and y becomes an ODE in eta bar. This is what I should see at the end of these manipulations. We will derive things, transform the boundary layer equations, and then we will come up with the ordinary differential equation, and then we will say, look, this equation which I have derived can be an ordinary differential equation if and only if. There will be a couple of conditions. Those conditions necessarily have to be satisfied for this eta which we have chosen to be a similarity variable. So, it is not some magic or something. For the PDE to transform to an ODE completely, certain conditions have to be satisfied by the coefficients that occur once we transform the equations. Certain conditions have to be satisfied by the boundary conditions that are transformed, and based on that we are going to say, look, after this transformation is made and if these conditions are met, then this equation PDE is indeed an ordinary differential equation. We all know stream function. By definition, u is equal to d psi by dy, v equal to minus d psi by dx. This automatically satisfies continuity. So, what are my boundary layer equations? We have Navier-Stokes equation, we have u du by dx plus v du by dy is equal to u infinity du infinity by dx plus nu d squared u by dy squared. This is your x momentum boundary layer equation. This was derived earlier. Okay, so now we want to write everything in terms of this stream function. So, u du by dx is nothing but d psi by dy, d by dx of d psi by dy, which is nothing but d psi by dy, d squared psi dx dy. Similarly, v du by dy would be minus d psi by dx, d by dy of d psi by dy is equal to minus d psi by dx, d squared psi by dy squared. And third one, nu, this is v, this is nu d squared u by dy square is nothing but nu d by dy of du by dy, which is nu d by dy of du by dy we have written here. This is from here. The u by dy was this d squared psi by dy squared. Therefore, it comes out to be nu d cube psi by dy cubed. 1, 2, 3, A, B and C. We will use this little later. And let stream function, now we are going to say stream function psi, let psi of x comma y is z of eta bar times n of x, and z prime of eta bar is u by u infinity, and z prime is nothing but dz by d eta bar. Okay, this is same. So, we are defining z prime of eta bar is equal to u by u infinity. Therefore, what we are going to say is dz by d eta bar is equal to u by u infinity. This is my definition. This is equal to, I substitute for u. So, 1 by u infinity into u is nothing but d psi by dy stream function wise, which is nothing but 1 by u infinity d psi by d eta bar by dy. Okay, d eta bar by dy. Now, stream function we said was n of x z of eta bar. We told this. So, d psi by d eta bar is nothing but n of x dz eta bar by d eta bar. What is this? This was nothing but your z prime, which is u by u infinity. So, this quantity in effect d psi by d eta bar is this. Left hand side was what? U by u infinity. Right hand side also I am getting u by u infinity. So, that will cancel. Therefore, I would get u by u infinity is equal to 1 by u infinity u by u infinity into n of x, this one, n of x is there, now that is going to come d eta bar by dy. So, u by u infinity cancels. So, I would write this as n of x divided by u infinity of x d eta bar by dy equal to 1, or in other words, d eta bar by dy is equal to u infinity of x divided by n of x, and this is nothing but your s of x. So, we will call this as a stretching factor. Now, you might ask me, what is u infinity of x? So, u infinity of x, typically for flow over a flat plate, we have free stream velocity is constant. Free stream velocity is constant, in which case your term here, this one, would go to 0. But in general, if you have flow over a curved surface, or if you have a situation where u infinity is not a constant, this term is essentially, where did this come from? This came from your minus 1 by rho dp by dx, right. So, this is the pressure gradient term. How pressure is varying along the flow direction is indicated by this term. So, this has a very important bearing on how the flow is going to behave. So, inertial force, pressure force, viscous force. So, dp by dx being equal to 0 is only for a flat plate, that is a special case. For a curved geometry, etc., you are going to have dp by dx, and that is why we are retaining u infinity as a function of x. Now, we say that u infinity, we have u is equal to u infinity dz by d eta bar. This was our definition from here. This was my definition. So, that is equal to d psi by dy. This is stream function definition. Therefore, d squared psi by dy squared. Why do I need all this? See, I have to transform all these. These are all partial derivatives. These now have to transform to regular derivatives of some variable z with respect to a new independent variable eta bar. It is a necessity because I want to convert something from an PDE to an ODE. So, I am doing this manipulation. D squared psi by dy squared, therefore, is nothing but d by dy of u infinity dz by d eta bar, which is nothing but, I apply, u infinity is not a function of y. So, it comes out u infinity d by d eta bar, sorry, u infinity d by d eta bar dz by d eta bar d eta bar by dy, and therefore, this quantity becomes d squared z by d eta bar. D eta bar by dy comes from here directly. Therefore, I can write d squared psi by dy squared is nothing but u infinity by n of x. Note, u infinity is a function of x everywhere. This times d squared z by d eta bar square, or in other words, u infinity x by n of x the whole squared dz d squared z by d eta bar square. In the next module, we are going to continue with this derivation and try to complete the similarity formulation, then proceed with the energy equation and try to get the similarity formulation for the same, and subsequently obtain the solutions for the ODEs. Thank you.